Hello everybody, and welcome to Lecture 31. So this is our last visit of the Power Series, and in particular, I'm going to be talking about Maclaurin and Taylor Series again. So we're going to be doing some more examples just to summarize all the topics that we learned in this unit. So here's our first example. We're going to find the radius of convergence of, and then the series is summation, n equals 1 to infinity. In the numerator, it's parentheses 2n close parentheses factorial. And then in the denominator, it is n factorial squared. And then off to the side, it's multiplied by x to the n. So for this series here, to find the radius of convergence, we would apply the ratio test. So let's go ahead and do that. We're going to define our capital L to be the limit as n goes to infinity. And what do I need to do with this a sub n? Well, in absolute value bars, what I need to do is I need to plug in the numerator here a of n plus 1. So I'm going to plug in an n plus 1 into all of these positions for n. So I would get 2 times n plus 1 in the factorial. And then if I plug in n plus 1 here, I get parenthesis n plus 1 factorial, and then all squared. And then this x to the n here would just be x to the n plus 1. So this is my a sub n plus 1 term. And then in the denominator for the ratio test, you just plug in a sub n. So this is just going to be 2n factorial divided by n factorial squared, and then times x to the n. So right away, I notice that x to the n plus 1 and x to the n, they're all going to cancel out except for I have one more factor of x in the numerator. And then think about doing keep, change, flip for this fraction. So this means that L is going to equal the limit as n goes to infinity. The first fraction, I'm going to keep that one. It's going to be 2n plus 1, so 2 times n plus 1, and that's all the factorial of that. And then in the denominator, I have n plus 1 factorial, but that's all squared, times, and I'm going to flip this the bottom fraction here. So this is going to be n factorial squared divided by 2n factorial. And I also have that x that's just still here inside the absolute value bars. All right, so I'm going to do my next step down here. I'm hoping to break things apart so things simplify. So how I'm going to do that is in the following way. So first, I'm going to write this as, I'm going to distribute this 2, and I'm going to have 2n plus 2 factorial. And then I have here, instead of n factorial squared, I'll do n factorial times n factorial. Then I'll do divided by, this here is n plus 1 factorial times n plus 1 factorial, if I have n plus 1 factorial squared. And then this is 2n factorial. This is all going to move outside of the absolute value bars. And then I'm going to have x still in the absolute value bars. And go ahead and squeeze in right here that you have the limit as n goes to infinity still. So all of this stuff is outside the absolute value bars because we know it's all positive. We're plugging in positive numbers for n. So this is certainly positive, so it can come outside the absolute value bars. We don't know if x is positive or not, so that's going to stay inside the absolute value bars. Now we're going to keep going, so we get the limit as n goes to infinity. I'm going to start breaking things up even more. So 2n plus 2 factorial. That's 2n plus 2, and then drop down to the next one, so 2n plus 1. And then what I have left is 2n factorial, so the rest of them. So then from here, I've split up this one. I still have n factorial times n factorial in the numerator. And then in the denominator, I can split up these n plus 1 factorials into n plus 1, n plus 1, and then I have n factorial, n factorial. So n plus 1 factorial is n plus 1 times n factorial. And I still have this 2n factorial here. And this is still times absolute value of x. So now I'm at a point where I'm just going to start crossing out a bunch of stuff. So all these n factorials in the numerator and denominator cancel. the 2n factorials cancel. And then what's the limit of this remaining piece where I have 2n plus 2 times 2n plus 1 in the numerator, and I have n plus 1 times n plus 1 in the denominator. So the limit of that is going to be the ratio of the leading coefficients. The coefficient on top is 2 times 2, because I have 2n times 2n is 4n squared. So I have a 4 on top, and then an n times an n is a 1. So this limit right here is going to be 4 for all of this portion here, except for this absolute value of x here. So I have 4 times the absolute value of x. So this is the limit here, and in order for this to converge by the ratio test, you need this to be less than 1. So we need for absolute value of x to be less than 1. That's the requirement to converge by the ratio test. If you divide both sides by 4, that means the absolute value of x needs to be less than a fourth. But what that translates into is you need the radius of convergence to be 1/4. So we're going to say the radius of convergence is 1/4. So it's centered at 0, and that radius is 1/4 in length. OK. For the next example, we're going to find the Maclaurin series for f of x equals x squared over 1 plus x. And we'll find its radius of convergence as well. So this was one of those standard power series that we first started with where you use the geometric series. So what you do here is you're going to use the fact that 1 over 1 minus x equals the summation n equals 0 to infinity of x to the n. And this converges when the absolute value of x is less than 1. So we're going to use this fact. So let's take f of x, which is x squared divided by 1 plus x. And we need to change it to look like this form. We need to get it to look like 1 over 1 minus something. So it's not 1 on the numerator right now, so I'm going to have this x squared is going to be out front. And I'll have 1 over 1. I have plus x instead of minus x like I need. So the trick that we learned was you do minus a minus x. So now we have minus x here, which is what we started with. And now this is in the form to use the geometric series formula. So this is the same thing as x squared. And then this part in parentheses becomes summation n equals 0 to infinity. And then this part gets plugged in, so I have negative x to the n. And this converges when the absolute value of negative x is less than 1. But that's equivalent to saying the absolute value of x is less than 1. I'm just going to write this a little neater and remind you of some of the algebra that you can do. So here I have x squared. If I have negative x to the n, that's the same thing as having negative 1 to the n times x to the n. And then I'm going to bring these two x's in here, the two factors of x inside. So I get summation n equals 0 to infinity of negative 1 to the n x to the n plus 2. Just multiply these inside. However, a lot of power series, what they do is they like to have it of the form x to the n. They like the variable to have just n for the power. So we're going to do an index shift. So I'm going to have x to the n instead. And if I went from n plus 2 to n, I subtracted 2 from the index, which means I'm going to need to add on 2 to my summation index. This is going to be n equals 2 to infinity. And then here, if you subtract 2 off the n index in here for negative 1 to the n, you'd get negative 1 to the n minus 2. But that's still the same thing as negative 1 to the n. It doesn't matter that you shifted it by 2. That's just going to generate another thing that looks just like negative 1 to the n. OK, so this right here, this is our Maclaurin series for this. And our radius of convergence is going to be 1. So we just take a look right here. And it depends on the radius of convergence for the geometric series. All right, now to finish off this set of examples, I'm going to use the Maclaurin series that I just built. And I'm going to use it in this application problem. So it says, use the first two terms of the previous Maclaurin series to estimate the integral. The integral goes from 0 to 0.2, and then inside the integral, we have x squared in the numerator, and it's divided by 1 plus x dx. So this is the function I just found the Maclaurin series for. So what I'm going to do is I'm going to have the integral from 0 to 0.2. I'm going to replace the function, the f of x, the x squared divided by 1 plus x. I'm going to replace it with the Maclaurin series I just found because they're identical. This is, at least on the radius of convergence, they're identical. This is n equals 2 to infinity, negative 1 to the n, x to the n, dx. And I'm going to integrate this. And notice I'm on the radius of convergence here. I'm within the interval of convergence. I'm from 0 to 0.2. That's well within the 0 to 1 as part of my interval of convergence. So then I can integrate term by term, and I'm going to get summation n equals 2 to infinity. How do you integrate with respect to x? You just take this x to the n and go backwards with the power rule. Negative 1 to the n is just a constant with respect to x. So this is x to the n plus 1 divided by n plus 1. That's how I integrate. And then what I need to do is I need to evaluate that from 0.2 to 0. And I'm only going to use the first two terms, that's what it says. And I'm going to take note of the fact that if you plug in 0, you just get 0. So really what I'm doing is I'm taking the first two terms of this expression, and I'm just plugging in 0.2. So this is approximately equal to, and let's take a look at the first two terms. The first term would be n equals 2. That's where the index starts. So if you plug in n equals 2, it looks like we get a positive 1. We get x to the third over 3. So that's what happens. And I'm going to do one more term, which would be the next one would be 3. So if I plug in a 3, I get a negative, and then it would be x to the 4 over 4. And I'm going to stop there because that's where they want me to stop. So this is an estimation of what the true integral is going to be. I guess this one up here is what we started with. So if you plug in 0.2, remember 0 doesn't matter here. You're just going to get 0.2 to the third over 3 minus 0.2 to the fourth over 4. And I'll let you know that that's 0.00226 repeating. And then a natural question arises here. If I have this alternating series and I use the first two terms to estimate, how far off am I from the true value of this? Like, how close does just using the first two terms get me to the true answer of that, like if you put it in a calculator? Well, the actual answer to this, I think I'll get to that. So first, let's use our estimation theorem. So if you recall, we have that estimation theorem. So by the alternating series estimation theorem, this estimate, the value I just found here, is off by at most the absolute value of the next term in the in the series. So I plugged in 2, I plugged in 3. The next one would be the absolute value of a4. So let's do that and evaluate it at 0.2. So what this is going to get me, if I evaluate it at 0.2, absolute value will get rid of this negative 1 to the n. And I'm going to plug in that 0.2, so I get 0.2. And if I'm plugging in n is 4 for the next one, it's 0.2 to the fifth. And then over 5, I have 4 plus 1. This is 0.000064, which in my mind, that's pretty close, right? So at most, this estimate that we found right here, it's off the true value of this only by this much right here. These, what is this, like tenths, hundredths, thousandths, 10,000, 100,000, 6,400 thousandths or something. So something very small. OK, so I went and I investigated. The true value based on a calculator is 0.00232,156. which is off by about 0.00005-ish. So we're off by just a little smaller amount than this. Welcome back. So now we're going to be doing this Taylor series example where I'm going to look for the third degree Taylor polynomial for the function 1 over x centered at a equals 1. So if they told me a specific degree of a Taylor polynomial, what I could do, if it's manageable, is just keep track of all the different pieces of information. Just write it out in a chart, and then assemble it together when I have everything written down. So that's my strategy for this one. I want to remind you that the formula for this is going to be summation n equals 0 to infinity, the nth derivative of f at a divided by n factorial. So these give us the coefficients for the Taylor polynomial. And you multiply this by x minus a to the n. So I'm using this formula that we've talked about before to build the third degree Taylor polynomial. So I'm going to need all the way up to my third derivative. So I need all these pieces of information. I need f of x. I need f prime of x, f double prime of x, and the triple prime of x as well, because I got to go all the way up to the third degree polynomial. So I'm going to assemble this chart really nicely, and then we're going to plug in everything at the end. So very methodical. F of x itself is 1 over x. You can think of that as like the 0th derivative. I haven't done a derivative yet. And if I continue, the first derivative is negative 1 over x squared. The next one would be 2 over x cubed. And then the third one would be negative 6 over x to the 4th. So I'm just doing derivatives one after the other. And then what I would need to do is I need to evaluate each of them at 1, because that's part of the formula. And my center is 1. So f of 1 is 1. F prime of 1 is negative 1. F double prime of 1 is 2. And f triple prime of 1 is negative 6. So these are all the pieces of information I need, and now I can go ahead and write out the final answer. So for a Taylor polynomial, usually you notate it like this. You do capital T, and then the subscript is going to be what degree it is. So this is T sub 3. And what is this equal to? Well, first I plug in 0 for n. So I would get the first derivative. It's the first derivative, or sorry, the 0th derivative at a. So f of 1 divided by 0 factorial. And then it would be x minus 1 to the 0 power. So that's plugging in n equals 0. And you have to go all the way to 3. So this would be plus f prime of 1 over 1 factorial, x minus 1 to the first power, plus f double prime of 1 divided by 2 factorial, x minus 1 squared. And then finally, if I can fit this right here, maybe I'll just do this to give myself some more room. F triple prime of 1 divided by 3 factorial, x minus 1 cubed. And that completes the third degree polynomial. Now I just plug in all my information that I've assembled. So the third degree polynomial, if I plug in all my pieces of information, f of 1 is 1, 0 factorial is 1, x minus 1 to the 0 is 1. So this whole first term here, it just becomes 1. Next, I get f prime of 1 is negative 1. So I get minus, and then 1 factorial is 1, and I get minus x minus 1 to the first power. Plus, this is alternating, right? The sign keeps flipping with these derivatives. The next one, my double prime of 1 is 2. 2 divided by 2 factorial is just 1. So I get plus x minus 1 squared. It's going to switch to minus, and it's minus 6. However, notice I have 3 factorial, which is also 6. So again, all these coefficients are going to 1. This is minus x minus 1 to the third power. So this is my third degree Taylor polynomial at 1. And now what I could do with this is I could use T3 to estimate the value for 1 over 1.2. So it's like I took the function 1 over x, I plugged in 1.2, and I'm gonna estimate what this is using this third degree Taylor polynomial. So what I do is I take t3 of, and I plug in 1.2. And what is that equal to? It's 1 minus 1.2 minus 1 is 0.2. Here I could just get 0.2s for these other spots. So this is 0.2 squared. And then minus here I get 0.2 cubed. So using this as my estimate, I would get 0.832. And let me just note that the actual value of 1 over 1.2 is 0.83 repeating. So there's how we use a Taylor polynomial to estimate the true value of a function at some specified center. So if it's a third degree or second degree Taylor polynomial, sometimes the best option is just to write out all the pieces of information and plug it directly into the Taylor series formula. My last example is a reminder that you can build Maclaurin series by taking a composition of known Maclaurin series. So we're going to find a Maclaurin series for f of x equals e to the negative x squared plus cosine. So what I have to do is I have to have you recall that e to the x, the Maclaurin series for that is summation n equals 0 to infinity of x to the n over n factorial, and then also cosine of x, that Maclaurin series is n equals 0 to infinity, negative 1 to the n, x to the 2n divided by 2n factorial. And both of these have an interval of convergence from negative infinity to infinity for x. So that's true for all values of real x. So both of them have the same interval of convergence. So therefore, I'm going to use this as my stepping stone to get to what I need. So therefore, f of x, which is equal to e to the negative x squared plus cosine of x, is, and for each of these, I'm just going to replace it with its relevant Maclaurin series. So for the first one, you plug negative x squared into the spot for x in e to the x. So all these x's there's only one x, right? It gets replaced with negative x squared. So I hope you're following that. So I write this series, summation n equals 0 to infinity. Instead of x, you plug in negative x squared to the n. So that's what x becomes. Everything else stays the same. Plus, I'm moving up here to cosine. I haven't even manipulated this at all. So this cosine is just going to become exactly the Maclaurin series I have, which is n equals 0 to infinity, negative 1 to the n, x to the 2n divided by 2n factorial. So this is this written out. What I could do, I guess, is just do what I usually do, which if I have a negative x squared to the n power, I could separate this as negative 1 to the n times x to the 2n. So separate that. And I'm going to leave everything else the same. I'm just going to rewrite the Maclaurin series for cosine exactly as it is. So that's it. That is a Maclaurin series for that function. I could take some time and write out the first few terms of it, I suppose. So let's look at just the first few terms. If you plug in 0, over here I would get 1, 1, and 1. And in fact, remember, 0 factorial is 1. Anything raised to the 0 here, a real number, is 1. It's same story over here. If you plug in n equals 0 for this one, you get 1, 1, 1. So the first term of the series, it's this plus this, which is 1 plus 1 is 2. Let's do one more. So if you were to plug in n equals 1, what would happen? Well, you would get a negative here. So we would get, let me start writing this out. So if you plug in a 1, you get negative, and 1 here would be negative x squared. But then it's divided by 1 factorial, which is just 1, plus, let's plug in the 1 here. You get a negative again, negative and then I get x squared. If I plug in the 1 for n here, and then I get 2 factorial in the denominator, which is just 2. So this is the term you get when you plug in n equals 1. So if I simplify that, I have 2 minus, I have 1x squared and another half x squared. This is minus 3 half x squared. And you can keep going. You can plug in n equals 2, 3, 4, 5. But the Maclaurin series would look like this. All right, so I hope that was a great way to review all the stuff we've been talking about in the last few lectures. After this, we're going to be moving on to different things. We're going to be starting to talk about arc length, and then we're going to move on to polar coordinates, parametric and polar coordinates. Reach out to me if you have any questions, and until then, I'll see you next time. Bye.